Hello, Stats class. This is lesson 7-2A, and you can do this before or after the 7-1 quiz. So this lesson is moving on to the next piece that's not on the quiz. So a reminder that in 7-1, we did general sampling distributions. The main point was to learn what a sampling distribution is. And so we looked at lots of different possible statistics and tested out what happens if it's a mean, what happens if it's a range or a max, or which ones are biased, and all of that was in 7-1. 7-2 and 7-3 are where we focus in on specific types, and those two most common ones that I told you about are the topics that we're going to do for the rest of this chapter. So 7-2 is about proportions, as you can see from the title. And then towards the end of next week, we'll start in on 7-3, which is means. So those are the two most common ones, and we're going to spend a lot of time on them for like the rest of the year because they are unbiased naturally, and so therefore they're really common and useful. So proportions are what we're focusing on now, lesson 7-2. And so we have to talk about what is the parameter versus what is the statistic, and we'll put both of those definitions here. The parameter is called P. I told you already that some books call it pi because Greek for populations. Parameter is the proportion of something in a population, or in other words, the number of successes in the population divided by the population size, which is capital N. And another way of expressing this is P is just the probability of success, whatever you've defined success to be. And that should remind you of some of the stuff we did in chapter 6 and 5 with probabilities. If there's 70% successes in the population, it could be expressed as a percent or a decimal, but the probability of success in the population overall, that's P. And what's interesting is this is a lowercase p, this is an uppercase p. They really mean about the same thing. P stands for proportion or percent or probability, and they're all very closely linked together. Statistic is about the sample, and we don't call that p, we call it p hat. And yes, it really is pronounced that way by statisticians, p hat. We've seen y hat before, and here's p hat. And it is the number of successes in the sample divided by the sample size. Divided by the sample size, which is lowercase n. And you could think of it as this is the theoretical probability and this is the experimental probability, which sometimes will be a little higher or lower depending on your sample. So if you take this p hat thing and you do it with lots and lots of different samples, you repeat it many times, and you plot it, what you get is the sampling distribution of p hat. Which is what we're going to be talking about today. What are the properties of that sampling distribution of all the p hats? If you plot each sample proportion separately, they'll sometimes come out slightly higher than the true probability and sometimes slightly lower, but they'll have a distribution that we can study. And so that's where we're headed with this part of the chapter. So properties of the sampling distribution of p hat. And as you might have guessed, we're going to talk about the same three things we always talk about with distributions. We're going to talk about shape, center, and spread, and I'll lay it out for you exactly what those look like. And some of this actually will not be a huge surprise because we've seen similar things before. Let's start with shape. So what's interesting about proportions is they're all based on the binomial distribution, because if you only look at the number of successes and you don't divide it by n, you've got a binomial distribution. So some of the stuff I'm about to say is the same as what we learned for binomial back in lesson 6.3. So that means that if p is smaller than 0.5 versus if p is equal to 0.5 versus if p is greater than 0.5 would make a difference in the shape. And you might remember from binomial stuff that we did before that the 0.5 is the one that's symmetric. In fact, it wouldn't necessarily be normal depending on the sample size, but it comes out close enough most of the time. So this would be symmetric with 0.5 being right in the middle and everything centered around that. Remember, proportions have to go from 0 to 1, so they always go from 0 to 1, and whatever's beyond that is impossible. Less than 0.5, greater than 0.5, so just picture what this number line looks like. If p, the true parameter, is less than 0.5, that means most of the p hats are going to be in this region less than 0.5, and maybe a few over here, but most of it's going to be on this end, and that would be skewed right. I had to stop and think about that. Because if p is less than 0.5, then p hat is usually less than 0.5. These are all the different possible p hats from different samples. And then the same thing happens in the other direction, 0 and 1 and 0.5. If the true value is bigger than 0.5, then most of the p hats would be over here and not so many on the other side, and that would be skewed left. And that's the same thing we saw with the binomial distribution. So this right here, binomial distribution stuff that I told you before, is what happens with small samples. But if the samples get larger, then this condenses down. And first of all, the shape gets smaller when the sample gets larger, which we'll see that in some warm-ups next week. But also the shape gets more and more closer to normal with large samples. And so we talked about that with binomial also. So this hopefully won't surprise you too much. With large samples, it gets closer and closer to normal. So approximately normal if the sample is large enough. And that large enough thing is if NP is greater than or equal to 10 and NQ is greater than or equal to 10. And we saw that before with binomial. This is the normal approximation to binomial. And if you take your binomial thing, which is the top of this fraction, and you divide it by n, that doesn't change the shape. And so the shape still would be approximately normal. It's based on what we learned about binomial distributions. So remember, n times p is the number of expected number of successes. If you have a sample of size n and a true population proportion of p, you'd multiply it to get the expected value. And then this is the expected number of failures. So that part feels like a repeat to me. We've done this before when we did binomial distributions, and the same thing happens with proportions, which is kind of nice. We've seen it before. I'm just reminding you that that same thing happens here. Center. Well, now that's almost the same as binomial. Not quite, because we're dividing by n now. I will say that what we want is for our estimators to be unbiased. We want p hat to be a good estimator of p, and what that means is that the mean would be the same, or the mean of all the p hats should match this. That's that unbiased thing that we've been talking about. Unbiased, if you want your center to be unbiased, p hat is naturally unbiased, but you have to make sure of that by doing random samples. So if you do random samples, which is what we hope for, and not biased samples, obviously, then what happens is mu p hat would be the same as p. That's the mean of all the statistics would match the parameter, which is the official definition of an unbiased estimator. So this is the mean, let's write it in words also, of all the p hats from all possible samples equals the population parameter or the population proportion of successes in the population. So that is the definition of unbiased. And I want to point out that this actually is closely related to the chapter 6 formula that we learned before. So slight little sidetrack here. Chapter 6, binomial distribution. I told you this is all based on binomial, and this stuff up here was based on binomial. What we had in chapter 6 was mu x equals np. Well, that's not quite the same, but remember, x is not the proportion of successes, it's the number of successes. So if you want to change it to, it's basically the numerator of that fraction. So if you want to change this to proportion of successes, you divide by n, and you get p. So if you divide by n on both sides, then basically x divided by n becomes p hat, and np divided by n becomes p. So that's where that formula came from. It's the same formula, except we're dividing by n now. All right, spread. Okay, so let's think about this. If you do a bigger sample, then you are more likely to predict your population well than if you do a smaller sample. And that's where the spread comes in. Bigger samples give you a smaller spread. And again, this is also going to be in one of the warm-ups that's probably not till next week. But you will see it happening, I promise, eventually. Smaller spread comes from bigger samples. And what happens is there's a formula for it. And actually, I'm going to show you the derivation first this time because it comes from the chapter 6. Remember, we had standard deviation of x, and it was square root of npq, where q is 1 minus p. I'm not going to write that this time. If you take this thing and divide it by n, I'm going to do a little bit of algebra for you. Remember, x is the number of successes. If you divide by n, you get p hat, which is the proportion of successes. Regardless, if I divide this by n, then I get mu p hat, which is square root of npq over n. Okay, a little bit of algebra. N could be rewritten as square root of n times square root of n. And then this one cancels. And you end up with square root of pq over n, which is basically the formula that I'm going to write over here slightly bigger. The standard deviation of the p hats, the sampling distribution of p hats has a standard deviation of square root pq over n. And again, that q, in your book, you'll see it written like this. That q is the same as 1 minus p. So now let's think about this for a minute. What happens if you divide by a bigger number? Bigger sample, that is, n is bigger. If you divide by a bigger number, you get a result that is smaller. That's what I'm talking about with this bigger samples means smaller spread. You're dividing by the square root of n. And that's kind of fascinating because we're going to see that again in another situation. Dividing by n makes it smaller, or makes it smaller if n is bigger. This whole thing and this whole thing is based on the assumption of a binomial distribution, which has to have independent samples. So this formula is true only if the samples are independent. So if each trial does not affect all the other trials, and that means you draw something out of the population and you look at it, and if you have a small population, we have a bit of a problem with that. Because this independence thing is harder to see on a small population. So the problem with a small population is if you're sampling without replacement. Let me just talk about that, and I'm not going to make you write it down. Let me write this down first. Oh, rats, I meant to say without, sorry. That's important. So picture yourself with a small population. Maybe there's 20. Maybe it's the same as the people in the class where we did the birthday thing on Wednesday. There's 20 people in the class, and you take one out and look at whether their birthday is before or after a certain date or something like that. Once you've taken that person out and looked at them, then the next one you take out would change the probability just a little bit because there's not very many in the population to start with. So if there were 10% of a certain thing and you take one out, then now there's not 10% anymore. That's a problem. So we normally only use this formula if we have a large enough population to not have to worry about that anymore. Or if it's a small population and we're doing it with replacement. So sampling without replacement is the problem. The large population, the difference is so small we can ignore it. So like imagine millions in your population and you take one out and look at it and that doesn't really change the probability of the rest. So the difference is so small we can ignore it if the population is large enough. And the official rule for how large is large enough is it has to be more than 10 times the sample. And we're going to come back to those conditions later on, and we're going to see them over and over again. We're going to see that the shape, we can only assume it's normal if this is true. The center, we can only assume it's unbiased if they're random. And the spread, we can only assume that it's independent if we have a large enough population. I'm going to write this in formula form also. This is n has to be less than or equal to, that's the sample n, 10% of capital N, which is the population, and that's sometimes called the 10% rule. So we'll come back, oh, sorry, didn't mean to cross off my stuff. We'll come back to those conditions later in the year, and they'll keep coming back. I'm just going to warn you. So I'm going to do one quick example and then be done for today, and that is an example of finding shape, center, and spread in an actual situation. So let's say my population is teenagers. I want to know the proportion who watch YouTube, which is probably like almost all of them. At the time that this data was gathered, it was 90%. Seems like it might be higher now, but I guess there's some people who don't, you know. And then out of this population of all teens, I don't know if this is in the US or worldwide, but either way, it's a huge population, right? We're going to take a simple random sample. Remember those from chapter 4 long ago of 1,000 teens. And we're going to ask them, do you watch YouTube or not? And I want to know if I find that proportion, which is a p hat, and I don't know what p hat is yet at this time, but if I'm talking about all possible p hats from all possible samples of 1,000, I could talk about the sampling distribution and I could describe it without even gathering any data. The sampling distribution of those p hats would look like this. Shape. Let's think about the shape. Is this a big enough sample to be, well, actually, let's start with this. P is greater than 0.5. So if it was a small sample, that would mean skewed left, right? But is this a small sample? Well, no, 1,000 is pretty big, and I could check and see just how big it is. I could do n times p is 1,000 times 0.9, and that's 900, definitely bigger than 10. But what's more important is n times q, because q is smaller than p, right? Q is 10%, so that would be 1,000 times 10%, which is 100, still bigger than 10. So because these are both bigger than 10, it's not skewed left anymore. That means it's approximately normal because these came out bigger than 10. So that's something to think about. If you get a big enough sample, you can assume it's approximately normal, and that's cool. The shape is approximately normal. I started off with skewed left because I do want you thinking about what would it be with a small sample, but then you can check this to see if it's big enough to get rid of that skewed left and change it to approximately normal. It changes with the sample size, which is kind of amazing. All right, center. Is it random? It says it's an SRS. Because it's random, that means I can assume it's unbiased. That means that the mean of all the p hats is the same as the mean of the population, which is 0.9. Because it's a random sample, which makes it unbiased. The official definition of unbiased is the mean of the sampling distribution is the same as the parameter. So because it's centered at the parameter, that's unbiased. And then the spread, standard deviation of p hat, that's that new formula I just told you, that's pq over n and then a square root. And that's 0.9 times 0.1 over 1,000 square rooted, which comes out to 0.00009. And when you square root it, you get 0.0095, really small spread because it's such a large sample. We could picture this as, well, we just said it was approximately normal, right? And the mean is 0.9, and the standard deviation is 0.0095. And it's okay to use this formula because my population is so huge that 1,000 teens is just a drop in the bucket, right? Because 1,000 is definitely less than or equal to 10% of all teenagers. So I want you to always be thinking in the back of your mind about, is it okay to use this formula? And this is why it's okay to use this formula. This formula is true because we did a random sample. This is not skewed left, but approximately normal because these things are true. So that's where we're headed with this chapter, is check to see if those conditions are met. There's 3 conditions for shape, center, and spread, and we're going to keep coming back to those until you know them so well. It's going to be amazing. All right, that is it for this set of notes.